Hey, welcome back. I'm just checking our stream connection to see how we're doing. And it looks like I have an excellent connection. And it looks like I have an excellent connection. And it looks like I have an excellent. Cool. All right, so happy Monday. We are into the second week, so we're coming up on the halfway point. So by Wednesday, we're halfway done with the class. Now we're starting to ramp up. Last week we had New Year's, so I didn't want to assign too many projects, and I wanted everybody to get used to submitting assignments. But now we're kind of doing like a whole module today and tomorrow, and then jumping into the whole next module, looking at here if we go into the month-long calendar. So last week we had a couple of things. Today, anyway, so today getting project 1 wrapped up and submitted, but also doing the readings and getting ready for homework 2, jumping into project 2 the next day. And then by the end of the week, we're already into module 3 so that we can finish up the whole class by next week. Whew. Pretty fast, but this is what we signed up for, right? Work hard, play hard. So we're gonna get through this whole 3-credit CompMech course in these 3 weeks. I saw some people resubmit some of their work from homework 1, which is great. So hopefully you saw like the comments that I had made, and hopefully that video that I created from Friday was helpful in coming back to revise that. So jumping into, so some people are probably already somewhat done with like project 1, others are maybe still working on it, and I'll after I review and add comments to everybody's work, I'll make the same kind of review video for this project. But I'll jump in here, and it's the same kind of steps that we were working on in the homework. So like looking at like using Python as a calculator, trying to take those calculations, turn it into like a function. And then this last part is looking at convergence of numerical methods. So we're trying this, and this is kind of something new in numerical methods in computational mechanics, is that a lot of times every time, if we're using a computer to solve a problem, like create temperatures at a given set of time, we're not creating a function, we're creating like a whole bunch of temperatures at given points in time. And whenever we solve something like analytically, so if I know that this is my differential equation, it has an exact formula, at least for that exact differential equation. This is the solution to that problem. And here, let's do a little bit of review. Come in here, grab this. So I'll copy that, put it over into our discard from last time. So this is my equation, and coming down here. Normally I don't like screenshots, but they're pretty helpful if you're just trying to do some quick calculations and math in this way. All right, so this is my analytical solution, and this is my ordinary differential equation. And the reason that I say that this is the solution to this problem, so if I look at dt as a function of time, that TA is constant, so it goes away. And then I end up with a t minus ta, which is also a constant. So I can leave that in there. So t0 minus ta times e to the negative kt. So derivative of that e to the negative kt is going to be e to the negative kt times k. Well, times negative k. So let's put this like that. So when I say dt over dt equals negative k times t of t, well, that's exactly what I just wrote in there. Because this whole thing, well, not that, this is that t of t. And then I also have this, like that ta term there, but I can plug that in. Plus like a constant where that ta is the constant that way. Or, all right, yeah, I can plug that in. Negative k times t minus ta, like that. All right, so I'll plug it in all the way, right? So this is a negative k times t0 minus ta e to the negative kt, like that. And that's equal to a negative k t of t. Sorry, this is t of t. So it's ta minus, or sorry, plus t0 minus ta e to the negative kt, and then all minus that ta, like that. So this ta, that ta cancel out, and I end up with negative k t0 minus ta negative kt equals negative k t0 minus ta e to the negative kt. And there, I've shown, like, yes, in fact, these are the same, that this solution is the analytical solution. But that's different in our, so let's grab just the equation, right? So just my differential equation. Now what I want to do for like these numerical methods, and we tried it with that population growth problem in homework 1, I can do the same kind of thing here with, so first what I'm going to do is say, let me think about like 0, 0.1, 0.2, 0.3, just all these, and up to like one hour, like that. So all these different points in time, and I know what the temperature is at that time 0. So t at time 0, and let's jump into our problem. T at time 0 is 85 degrees, and that, so we'll say 85. So when temperature is 85, the slope is negative k times 20. So I know at that time, I know what temperature is, and I know what the slope is. So I can take that slope, move forward, and say that, and really this is kind of like, I don't know what happens in between 0 and 0.1, but I'm making an approximation that it's a straight line for that whole time. And that's what this numerical method is doing. So once I get there, then I can make another slope and go to 0.2. Until I get all the way out here to like 1 hour, just like that. So the numerical results is not, it's not a function. I can kind of look at it and say that it looks like this function, that it has the same kind of like exponential decay or something, but when I'm looking at the numbers, all they are numbers in here. And it's kind of cool that you can even do this and that it works. And the smaller I make, so if I take 0.1 and make these go like 0.05 hours or smaller, like 0.01 hours, make it 10 times smaller, then it's going to get closer and closer to this exact differential solution. And the nice part here is that the process is always the same. It's always the same integration process. I can always say that so T is some like lin space 0 to 1, and we'll say like 61 if I want to do every minute. Well, there I did 11, right? So dt is T1 minus T0, and now for I, well, first we'll set up our T np dot zeros of length of T. My first, I know the first temperature, that it's 85, and now for I in range of 1 to length of T, I can say T of I equals T of I minus 1 plus that dt times that delta T, where I know that this is negative K times T minus A. I was trying to do this guy. Give me back my pencil. And that'll populate all those temperatures, and I can compare that to this problem, to like this solution. So now I've got a numerical. So this is my numerical solution and my analytical solution. So analytical doesn't change. I can plug in any time I want and I'll always have the same answer, whether I take time steps of 1 hour or 1 millisecond. It's always however fast I step through, versus numerical, where it does depend on how big of a time step, like how long am I integrating, like how long did I say the slope was constant. If it's a small enough step, then it doesn't matter. If it's too large, then it does start to matter. Yeah, so, and yeah, we might as well try it out. Let's see if it works, right? All right, so I'll say t goes from 0, let's do 3 hours, and we'll say every 10th of an hour. And in case you're if I could spell Lin space like that. In case you're wondering about why it's 31 and not 30 to get time steps of 0.1, it's because I need one extra. I need one to describe 0 and all the way up to 3. And that way my time steps are 0, 0.1. So I want 1 for 0 and then 30 for the rest of them. Or I could use a range works okay. A range, I would start at 0, go to 3, and I think I would say my step size is 0.1. The only problem is it'll cut off the last value here. So I could say like add a 0.1 there, and that way I'll get that last step here. A range is not supposed to work with fractions like that, with non-integer step sizes. Most of the time it works fine, but if you're going to use a range like this where you're defining dt instead of having dt defined based on linspace, then just double check. Make sure that the min and max values of time are what you expected, and the step size. I mean, step size is going to be whatever you gave it, but make sure that min and max are where you thought they would be. And I think as long as it's more than, like if I do 0, 5, as long as it's more than 3, it'll go up to, but not include that last step. And this is kind of general Python inputs: start, stop, step size. And this is also like start, stop, but number of steps. Anyway, okay, so we got time is always an independent variable, whether I'm talking about like an analytical solution or I'm trying to solve numerical solutions. I can define time to be whatever I want. Here it makes sense to start at 0 and go to 3, like 3 hours, but I could define it for any case. My time is going to be the same. All the temperatures are going to be the same shape as time. So I want it to be an array, and I want that array to be the same shape. And then I want to say that first temperature is that T0, 85 degrees. And now for I in range, length of T. Oh, and we want to skip the first time step. So don't start at 0. I want to start at 1. And now I can say Ti is Ti minus 1 minus K times T bracket I minus 1 minus T ambient, which is 65. Yep, 65 degrees times that time step. And I haven't defined K yet, so yeah, let's go in and jump. Let's try that out. dt. So this slope, I have 2 data points, right? I have an 85 degrees and an 80 degrees divided by 3/4 of an hour. So is 85 minus, or sorry, it should be 80 minus 85 divided by 0.75. And then K is going to be that dt dt divided by my current temperature. So I'm going to say current temperature is 85 minus that ambient temperature, 65. And if you're already working on this project, you might be looking at this and saying like, well, oh no, I used 80. Maybe I'm wrong. And it gives us two different values, right? So whether I say it's 80 or I say it's 85, it's either 1/3 or I forget what 0.44 is, but it's different. So the question is, when I'm saying that T over here on the right side, should it be 80? Should it be the temperature at time 0, or should it be the temperature at 45 minutes? And the answer to that comes back to what we were just talking about here. So if I say, so here's my 85 at 0. Here's 45 minutes where it's 80. So this slope is not going to change. That was a terrible slope. That's always going to be the same slope. But if I say that and we'll call that dt over dt. If I say that this is the case, then that's saying that the next time step is defining the slope. So that's called a forward difference method. If I say dt equals -k times t of 45 minus ta, well, this is saying that the previous step is defining the slope for that dt. Both of them are correct, but they're both equally wrong. So that bothers some people. So one thing that you can do, calculate k for both of them, take the average. But it's up to you, however you want to deal with it. But we're introducing a little bit of error because we're taking an exponential curve and saying that it's a constant slope for 45 minutes. Anyway, so now I've got k here, and I can actually integrate this thing and look at, I start at 85. Oh, and I messed up this sign, didn't I? -k. Oh, because, yeah, this should be a negative sign here. So it should be a positive k. So it starts at 85, and by the end of 3 hours, I get down to 72 degrees. Let's take a look at what that looks like. Like this. I'm going to add some markers to it so I can see what that looks like. And right now, I'm showing that, yeah, I can do it. But if I change this, make it more time steps, and I don't want to print out all those. It seems like it's different, but I don't know how different it is. So one way that I can show how it's converging, so that's the main thing here, is like when we talk about converging for numerical methods, it's not talking about like as temperature goes to infinity. That's a different like steady state convergence. What we're talking about is as that time step decreases, how is that affecting my solution? Is it getting closer to this result? Is it getting farther away? Like, what's happening? So let's take this and merge it up here so it's all one thing. And I'm gonna take this whole, oops, not like that, take all of this. So if I can do something in Python once, I can do it as many times as I want. For n in, and we tried 31, we tried 301. Let's also try like 7, 11, like that. And instead of saying that this is a constant, we're going to let it be n. And now I'm going to start using multiple lines here. And I'll create a label that uses that time step of however many hours that happens to be. And it's a little hard to see. Maybe we want to flip. Flip the direction, kind of like go from large to small so that the smaller ones are on top. And what I can see now is that as I keep decreasing, so as the time step keeps getting smaller, it gets closer and closer to that blue line. So everything, and then the last thing that I could do, if I'm trying to show like, hey, it's converging to that result, is plot I want to take this function, so 65 plus 85 minus 65 times np.exp negative k times t, like that. And we'll make this one a black solid line. And now I can see that the smaller those steps get, the closer it gets. See, for these blue squares, they're lying directly on top of that black line. So now I've shown that, yes, indeed, this thing is converging. And I could look at the error, like how close were certain values or something, but visually it makes sense that we're doing a good job converging to that final result, whether we take half-hour steps or like 0.1 hour step, 0.01 hour steps. Cool. All right, so hopefully this helps as you're working on this project, and I'm looking forward to reviewing and kind of helping the next steps there. All right, have a great day, and then we'll be working hard on module 2 all day tomorrow, and I'll try posting another video on some of the analyzing data and loading data sets and using like some data science, then even some Monte Carlo methods of like generating our own random numbers and trying to make insights based on that. Okay, thanks again, and I will see you next time.